Okay, I've got an MDP YouTube account.
Yeah. I think it's gonna work. I mean, the streaming's working fine probably, but it's not. So this has a mic.
This is like a selfie style camera. So on your own screen, when you lean to the right, it looks like it's leaning to the right. And that's why they do the flip. Because otherwise, when you lean right, the image would move to the left.
Yeah, but it's only in Hangouts. I tested this like.
Oh, really?
And
because Hangouts
Zoom,
is assuming you're doing video chat with.
Probably, even though it's Hangouts on air, which is supposed to be for streaming. So like doing like QuickTime or Zoom or any of that stuff.
Yeah, Zoom is what we use
plus
for
it's not picking up on the mic and the camera.
He can do. We've got a pretty loud.
Yeah.
This is so, because what's his mic's not going to get
Nope. Gotta love Hangouts.
No, and that one's not either. This big enough?
Yeah.
Yeah. Is it a wireless camera or wired?
Wired. I wouldn't worry about it too much.
You got a timer up there, I can tell. It still says 0. Yeah.
I wouldn't worry about it. I doubt anyone will join anyhow.
Well, he's really happy to see the Yildiz
I know.
Adu knocked to Dirk. I can't read backwards. That
Yeah.
Actually backwards? It's no. Well,
Yeah.
Yes.
Yeah. Hangouts.
It may not send it to them backwards though. It might just be like I was saying.
That's true.
That
Let me see.
Quick, everybody join the live stream. Did you say Hangouts or YouTube?
Oh, yeah, it's
Yeah,
showing in the right direction.
It's just so that it
Good.
doesn't look weird to you when you lean sideways.
Yeah.
Cool. Oh, I guess we can test the audio then too, huh? Lean sideways.
Yeah.
Turn up your speakers, Wes.
Oh, I guess we can test the audio though too, huh?
Turn up your speakers, Wes.
Oh, I guess we can test the audio though too, huh? So, it happens in meetings a lot. Getting the remote employees and they forget to turn their speakers off. I used to do that with
You can start now, Jared, too. Okay.
well, this is one of the engine quilt chairs in this one. Based on backwards of the little stick thing that you pull out. How was your job? No, that one was. That's the working chair. So.
Okay, get started. So, happy New Year, everybody. I thought I'd start off by doing rock solid and mentioning that the CFP is open until February 8th. It doesn't sound cool.
Not this week.
So yeah, so you should sit, talk to Big State Con for the summer. I've done it a couple times. It's a pretty good conference. So today we're going to be talking about production WebAssembly and kind of go into the details of what it takes to get a WebAssembly module integrated into a production application. So for those of you that don't know me, my name is Jeremy. I work here in Bozeman at Iron Core Labs. We're a data security company startup here in town. So with WebAssembly, a lot of times when you look at examples on the web, tutorials like how do I get started with WebAssembly, you'll see code that kind of looks like this. It's like, hey, here's how you do Fibonacci sequence, and then you can run this in JavaScript. And so they'll show you how to take this and compile it to a WebAssembly module. They'll maybe show you how to load it into a browser and actually call it, and then it's like that's it, the end of the article. And so like that's cool, but that didn't really give me any information about what like I'm really to do here. It's like that was a neat kind of example, but it doesn't really kind of dive into a lot of details about like how you actually do more things that WebAssembly module. So the goals kind of we're going to cover here are how to compile an existing Rust library into WebAssembly. You can use it in a bunch of different languages, obviously. Rust is pretty high up there in terms of the usable languages that compile WebAssembly. That's what I have experience with. We want to be able to pass complex arguments to this module. Just passing numbers for Fibonacci sequences isn't really cool. That's not really something you're going to need to do very often, so we want to be able to pass more complex things. We want to load into an existing web app, so we have an existing JavaScript code we want to integrate this into, and we want to use this WebAssembly module from within a WebWorker as well. So these are the things we're going to cover as part of this talk. So to give you a little bit of background on kind of what we did at my work, we had a library called Recrypt. It was within Scala, and it's a cryptographic library. And we had that core library within Scala. We took a tool called Scala.js and compiled that Scala to JavaScript, and it produced a lot of JavaScript. It was like 400 and some K or something like that of JavaScript, but it worked, and it allowed you to just load like any other JavaScript module and call it and do whatever you needed. And so then we took that module and wrapped it in an SDK, and we're able to move forward with that. So that worked out. Performance of that was hit or miss somewhat. So the operations are kind of irrelevant here, but point being is that some operations were pretty reasonable, some were pretty bad. Over a second for some things that was not super great. And so that was like hey, this works, but it's not really feasible for a lot of people. And this is obviously kind of why we talked about doing stuff in WebWorker here, because you can't just like freeze up the main thread on the UI for over a second doing some of these operations. So from that, we decided to move from Scala to Rust. And so there was kind of a couple reasons we decided to go to Rust. One of the main ones was the portability of Rust. We sort of wanted a single core library. When you're writing cryptography, you don't want to have to like maintain 10 libraries in different languages and have issues in all of them, or have to get audited in different places. So we wanted to be able to have a library written in Rust that we could then compile to binaries and be able to use from almost any other language. So So that's what Rust is really great at, is being able to kind of compile it into a machine code and be able to use it from anywhere. And then obviously the other big thing was performance. So we knew that we could get better performance out of Rust than we could out of probably not only Scala, but also just, doing Scala.js cross compilation as well. We could take that Rust library and move it to WebAssembly, and the entire point of WebAssembly, a lot of the time is for performance and be able to improve how fast things are on the web. So the challenges we get faced with this. So by default, today, WebAssembly only supports 4 data types. They're all numeric. You can pass 32 and 64-bit ints and floats, and that's it. They took the WebAssembly approach to be a very minimal, like MVP style thing, where it's like, yep, we'll just keep evolving this over time, but at its base, this is kind of like very much MVP style of what they have. We also need to fall back to JavaScript browsers don't support WebAssembly. So luckily, that only is IE these days. Edge, Safari, Firefox, and Chrome all support WebAssembly natively, and IE doesn't, obviously, because IE doesn't support anything. But I11 was still kind of like in that, we need to support this for the time being. So we want to be able to fall back to our previous Scala.js library when we don't have support for WebAssembly. And then obviously we want to be able to use this within a web worker. And so we're using Webpack to build this SDK. And so, we need to be able to pull in WebWorkers as part of this. And so we already were doing this with Scala.js, but you added that and do this with on top of having WebAssembly modules as well. Okay, so the first thing was complex data types. I did this presentation drawing for my wife. She's like, white crackers. And I was like, I don't know. Like, what stock form do you use for complex data types? So anyway, she's like, I always have reason. Okay, so the tool we're going to use for this is WebAssembly Toolkit. This is a toolkit that allows you to more easily interface between your Rust code and your JavaScript code that wants to call in WebAssembly. So there's 2 different parts of the WebAssembly Toolkit. There is an actual library in Rust that allows you to marshal data between JavaScript and WebAssembly. And then there is a CLI tool that allows you to, after you have your compiled WebAssembly, to generate shims for you that make interfacing with your WebAssembly module easier. So in a lot of ways, this toolkit could, in theory, go away over time as WebAssembly gets more useful and more usable. But for now, it's kind of like a nice toolkit to be able to let you more easily interface with WebAssembly. So the way that sort of looks is we have now a cryptographic library written in Rust. So Recrypt.rs, as we call it. And so what that is basically just a pure Rust library. You got a Rust code, you can call it this thing and use it just like anything else. And so you end up writing a chunk of Rust code that's basically a layer that sits around that library. And so what this layer is responsible for is accepting data types that are come from JavaScript, converting them into Rust data types, and then calling the core library if you want. And so it's sort of just basically a marshalling layer. So it's a pretty thin wrapper, but there's some data conversions in there between WASM and WineGen. It discloses like JS value types, which are just like generic JS values. And so you can take those and cast them and convert them into Rust types, and then you can pass it to your Rust module. So once you have those 2 things together, you can compile them together, and you have a WebAssembly module. This is an actual .wasm binary file that you have. And so that is only partially usable, really. It's kind of like, yeah, you can interface with it, but it's pretty clunky and it takes a lot of work. And so the WebAssembly Toolkit will generate you a JavaScript code-based shim that sits on top of that. And so this is all auto-generated based on all the functions you have in there, so it generates this code when you run your compilation step. And it dumps out this shim layer, and that's the layer you actually interact with. And so all the functions and such that you write in your WebAssembly module, they have equivalents in your JavaScript shim, so you interact with that, and then that is what is actually responsible for interacting with the WebAssembly module. And so that makes it a little bit easier to interface with these things and be able to do things like complex types. So as I mentioned, we only have numbers, right? That's not super useful. So the WASM WineGen shim allows you to do more complex things, and it does that via serializing the data between JavaScript and WebAssembly. And so anything that you can JSON stringify, you can now pass between JavaScript and WebAssembly. So, arrays, objects, things like that. You can't do functions. There's other ways to do functions through WebAssembly, but everything that can be JSON stringified and serialized and deserialized in JSON can be now passed between these two things. So the way that works is a little bit janky, hacky, but you don't have to deal with it, which is nice. So say you want to pass this object from JavaScript into WebAssembly. So what this will do, you'll call a function in the shim and say, here's my object. It'll take that object and it'll JSON stringify it, convert it to a string. Then it'll use get and code that, convert it to bytes. So now you have just an array of numbers. Then it'll jam that array into the WebAssembly memory at a specific index. And then it'll pass that index and the length into WebAssembly. So, hey, numbers, they're just numbers. So all the calls you end up seeing between JavaScript and WebAssembly, they are also numbers, but in a lot of cases it's basically like, hey, this is the memory point you need to access, here's how long it is. And on the WebAssembly side, it'll get that and say, okay, cool, go into memory, pull that out, and then reverse this whole operation, and now you have some representation of that object in Rust. So, obviously a little janky, but again, you don't have to do this yourself, it just kind of does it for you. Obviously, as you probably would see here, the one thing about this is that you don't want to be passing large amounts of data back and forth, because you're obviously doing a copy of this every single time. So you ought to be kind of cautious of like memory consumption here for that. But yeah, this allows you to kind of do any complex type you want to do. And so, like I said, you can pass kind of whatever you want, support higher types than just in the use. Okay, so now we have a module that we can pass complex types to. Now we need to load it into the browser. So when I started using WebAssembly, it was pretty amazing to see how much they've been iterating on it in the short amount of time that it's been around. So this is how originally you were supposed to load a WebAssembly module. You would make a fetch to your Plaza module, then you would get that back converted to bytes. Then you would take those bytes and call WebAssembly.instantiate with those bytes, and then you would take that result, and then that would give you your instance, and then you could call results.instance.exports.whatever function you have on there. So this and like there's actually even a couple more flavors and ways to do it here. There's like actually a WebAssembly.compile step, like instantiate, compiles, and creates an instance for you. So the one thing that this does that might not be obvious is that you can create multiple instances of your WebAssembly module in a single JavaScript code base. You can download the WebAssembly binary once and create multiple instances of that, whatever code is in that module. So if you need more than one, you can do that too. Luckily, that's been simplified to just something that looks like this. So now we have an instantiate streaming, which not only is this simpler, but it's also faster because it compiles and creates instances of it as it streams in from the server where you're pulling this from. So you just pass the result of your fetch operation into this instantiate streaming, and when that's done, it'll give you an object. And so that's sort of one of the better things of WebAssembly as compared to JavaScript. The startup time is that with JavaScript, it has to download the entire thing, then parse it, and then execute it. In WebAssembly, you can basically start compiling it or parsing it at a time, like as bytes come in. So your time for like first operation is a lot faster with WebAssembly than it will be with JavaScript. So luckily, you don't have to do any of this because if you're using things like Webpack, it supports WebAssembly natively, the later versions of it do. And so all you have to do is configure your Webpack config to say, hey, I want to be able to support .rasm files, and that's about it. It'll auto-generate all that code for you. It generates basically conditionals depending on what the browser pulls in terms of how to instantiate or compile things. But you don't have to do anything. You just kind of say, hey, I want to pull in WebAssembly, and it's like, okay, I'll do all the compilation for you and just give you the result at the end. And so then, all you have to do is use a dynamic import. And so in this case, you can do a dynamic import to a direct.wasm file, but in our case, we have the shim, and so you actually do a dynamic import to just the JavaScript shim, and then that will obviously pull in the WebAssembly module underneath as well. And so obviously, you can't, the reason this has to be a separate import is because this is an asynchronous operation, because you can't obviously bundle WebAssembly with JavaScript, right? You have to have a split point where you load some other piece of code. You can't combine binary WebAssembly with text-based JavaScript into a single file. You have to have a set of files, which is why you have to have
base64 encode WASM
That
feed
is,
into a
that is a
string,
thing, sure, yeah.
decode it, and then feed it into the streaming.
Yeah, that is, I think there's examples doing that.
Let's see if that gets through code review.
So what you'll end up seeing when you run this is you have your main JavaScript app, kind of your startup bundle there. And when you load this thing, when you call it import, you'll see two separate requests go out. One to load the JavaScript shim, and another one to load the actual WebAssembly binary. And so when that resolves, when you get back this promise with the WASM module, again, you're interfacing directly with that JavaScript code, but it's doing all the work for interacting with WebAssembly. Okay, so now what about when WebAssembly isn't supported? Well, it's basically the goal I had for trying to do this was to make it as basically as opaque as possible. That when I'm trying to load this module, I don't really care whether it's WebAssembly or JavaScript. I just want to load this thing and I want to call functions on it, right? And so my goal was basically to hide all these details, the implementation details of how and where am I getting this thing. I just want to be able to load the module depending on what's supported. And so that ended up with some code like this, where we have a conditional that dynamically imports either the JavaScript shim or your native JavaScript bundle. And then you export a function that basically returns that promise. And so everybody who wants to be able to call into that just says, okay, load this module, and then when that returns, they'll have the module they need, whether it's JavaScript or whether it's WebAssembly, you don't care. It's all hidden from you, like how the implementation works. And so checking if WebAssembly is supported pretty easy. It's just runtime type checks and whatnot that you're probably used to if you write JavaScript. Yeah, and so then as a consumer, you'll only get one of these imports at a time. Right? You'll never load both modules when you're visiting whatever site loads this stuff. Whether you get a WebAssembly request or you get a JavaScript request, you won't ever get both, which is another kind of goal there. Is like don't load code you're not going to use. So then your code kind of ends up looking like this. You have sort of like a module loader code that lives in your bundle, your main bundle or wherever it is, and then it'll either conditionally request your JavaScript library or it'll request your WebAssembly library. And everybody who wants to call into this thing just uses promise-based asynchronous code and says like, load this module, don't care where it comes from. When it comes back, you can use it and run your methods on it if you want. And so the nice thing obviously with promises is that'll all be cached, right? So you can just call load module as many times as you need. It'll always just, for most situations, it'll just immediately return. It'll only be the first case where you want to load it, but it'll actually take a little bit of time to load the code. Okay, so now WebWorkers. So this is probably going to be a pretty common thing. Most WebAssembly code that people write is usually pretty processor intensive, right? You're usually not writing code that's equally fast in JavaScript. And so if it was, we'd just write the JavaScript anyway. And so a lot of things like in our case cryptography or things like game engines and that kind of stuff, like most of the stuff you're going to be doing in a WebWorker or in a WebAssembly module, it's going to be a lot faster in WebAssembly, but there's probably still some time there where you want to make it be on a separate thread and not have to be freezing up the main UI whenever it's running. So Webpack has a worker loader module that helps you automatically load WebWorkers and makes it super simple. It does not have support for WebAssembly yet, so you have to use the native browser worker API, which isn't too awful, but it has some kind of caveats. The one nice thing that the worker loader gives you is it'll automatically do cache busting for you. So when you build for production, it'll generate a hash and say, okay, your worker JavaScript file has some MD5 hash or whatever, so it'll cache bust every time you make updates to it. So you have to kind of manually do that yourself with the native worker API. And so the way that looks is like this. When you create a new worker, you just give it a path, relative path to your domain of where your WebWorker code lives. And so obviously you want this to be a little bit more dynamic. You don't want it to be fixed because otherwise it would not be, you would be cache busting and all kind of benefits there. So the way I ended up implementing this was having a constant where I dynamically say like, hey, I'll tell you at runtime where this worker URL is going to come from, and then use the Webpack define plugin to say, okay, in development, it's just going to be a fixed path to this worker file, but in every other environment, I'm going to have it point to some hash root. JSON certify app that actually has like a version of it or some sort of other cache busting thing. And so then I'll just replace that thing. At that point then, from your web worker, you can easily load all your WebAssembly stuff, just like I showed earlier. So once you have that implemented, it ends up looking like this. So you have your main app bundle that has WebWorker code in it to be able to create your WebWorker and pass messages back and forth to it. Your WebWorker has now the modular code that says, okay, what am I loading WebAssembly or am I loading JavaScript? So you may not have this, but in our case, we had to write little shim layers on top of all of our JavaScript and WebAssembly so that those interfaces are identical. Because every time you have that split between your WebWorker and your JavaScript and WebAssembly, you want those interfaces to be identical. And so if like the functions don't take the same signatures, you need to write like a layer on top of that. So that might be optional, might not be depending on how close your WebAssembly code is to your native JavaScript code. And then on the WebAssembly side, you have obviously another request for the actual binary itself. So in terms of when you run this in Webpack, you end up getting these different bundles. You have your app, you have your work. Like at a minimum, obviously this is like a minimum you probably have. You have your app, you have your worker, you have your native JavaScript all rolled into one. You have your WebAssembly shim, and then you have your WebAssembly module. So that kind of makes it feel like a lot of work, and like that's really way too much to do. But the question basically is like that's a lot of overhead and complexity. Like, is it really worth it? Well, I mean, at least for us, like absolutely. I mean, we had some time on this beforehand, before we did all this work here. But to give you kind of a sense of what we're talking about, in Chrome we saw actors for just these functions. There's a bunch of others, but it's roughly the same. There's almost a 50% increase in the time for all these operations. And you can see, in this case, like we're under 200 milliseconds for every operation, which is much better in terms of, like yeah, it's still something you want to do with a web worker, but fast enough that people aren't going to be like throwing their machines out the window. So it turns out Chrome is actually the slowest of improvement. So I mean, other than Edge, which I don't really count, every other browser is actually better at WebAssembly than Chrome is, as far as we can tell. So Firefox has almost 1,000% improvement, and Safari is actually over 1,000%. So that was sort of surprising to us. I would have thought Chrome would kind of been. I mean, I kind of expected Firefox to be up there because they like are pushing the standard forward as well as doing WebAssembly, but I didn't expect Safari to be this good, or Chrome to not be as good, I guess. But your mileage may vary. Obviously, there's a lot of ups and downs in a lot of this stuff, right? Like, I mean, one of the things we found was that the crypto library we had in Rust was all compiled for 64-bit machines, which is, who doesn't have a 64-bit machine? But WebAssembly only runs in 32-bit, and so if you actually compile it for 32-bit for WebAssembly, like you get some really good performance improvements, but then you make everything else really slow, and so you kind of have to, compile it for different, and Rust supports this. You can basically target different environments. You can say like, when we compile this, we say we're targeting WebAssembly, so we can be like, oh, okay, well in that case I'll go to 32-bit. Everything else will go to 64-bit. So again, there's a lot of like malleability with these performance numbers. So what's next? So ideal life, eventually you want to do a lot of this because you'll just be able to say, I'm just doing WebAssembly, and that's it. Also, WebAssembly has this concept of threads, which are available in Chrome 70. They're not really like what you would hope would be for threads. I mean, a lot of the examples are like, oh yeah, like you just do pthread create, and it goes off and does this thing, and like that would be super cool. But it turns out the way that's actually really implemented is it just says like, oh well, we'll just shove that in another web worker. And it's like, well, okay, I mean that's a way to do it, but it's it would be really nice if like just purely in Rust you could say, or any other language you could say create a thread and it would just do that, and you wouldn't have to like have all this overhead like another JavaScript wrapper and another JavaScript module. So they're definitely, again, they're very incremental, like how they're moving these things forward and doing it very piecemeal. And then garbage collection. So WebAssembly doesn't have garbage collection today, and so that's basically a requirement for what they're moving before they're going to support additional data types, like being able to natively pass structs, arrays, strings, that kind of stuff into Rust. And so they're kind of holding off on doing all that support until they get actual garbage collector into. And so the way it's actually going to work is the WebAssembly will just use the JavaScript garbage collector. And how that works, I don't really know exactly, but that's basically what they're going to do for the additional types. And so you can do all this stuff today, but like I said, kind of when we talk about the loss of binding and stuff, the hope is that all just goes away, right? That's very much just like a polyfill layer today for something that hopefully will just be supported natively at some point in the future. So it's getting there. It's just being very methodical about their approach to how WebAssembly works. That's it. Thank you. Is there any questions people have about anything we did?
Can you detect from the client side the 32 versus 64 and have two different compiled files and pick the one that matches the architecture of the machine?
It doesn't matter. For WebAssembly, it doesn't matter which machine running. WebAssembly is only 32-bit.
Okay.
Yeah. It has no bearing on because the point of WebAssembly is it's like, I mean, I didn't really read up on like the history of that decision necessarily, but WebAssembly is meant to be like super portable, right? Where it's just like you compile it once, works everywhere for the whole Java thing, I guess. So yeah, why they did 32 and not 64, I don't know, but yeah, it doesn't matter which machine runs, it's always 32-bit. I mean, I guess if you were at a 16-bit machine, it probably would work.
Do you guys worry about like having to maintain two APIs essentially with your Scala.js and your Rust?
Yeah, I mean, that's sort of one of the reasons why we mentioned Rust to begin with, was it's like, okay, we'll do two, but let's hope that we don't do any more than just those two, right? And so we have to support the Scala one for a while, right? Because we need you can probably compile Rust to JavaScript. That's probably a thing. Everything compiles to JavaScript these days, it seems like. But we've already put our Scala library out there. It's been audited, and so that'll be supported for quite a while, probably. But there will be a point eventually where it's just like we break and say, okay, we're not going to have features to this thing anymore. Like we're just going to say, yeah, it's out there, it works, but it's like no longer.
Would you have to take a different approach then with like the split in your shell?
Yeah, I mean, we probably wouldn't do that until we decided to drop support for it. So, yeah, how long is that going to be?
I don't know.
It's like iOS, I think, still has more usage of Edge these days, unfortunately. But it'll be, I don't know how many people saw it, but like they're moving Edge over to be Chromium based, and so there's a lot of things that like Edge doesn't support. Like I mentioned this in like one of my previous talks that the WebWorker API, where you do various crypto operations and generate random numbers, like doesn't exist in a WebWorker and IE or an Edge, and so you end up having like every time you want some random data, or every time you want to generate random data in Edge, you have to go back to the main thread, ask for random data, and pass it back to the worker, and do all this kind of back and forth. And so there's a lot of like just real headaches for maintaining that will hopefully go away with the Chromium thing. But there's a lot of details about what they're doing there. Like I've heard them talking. It seems like they're basically going to like roll it out as Edge 19, and it's a different like hopefully it won't be some like new browser that they just like try to abandon Edge and then, let's do things. It's like, well, how that work real well without IE, obviously. So, yeah.
I had a question.
Yeah.
So I think I read that Rust pairs well with WebAssembly because of the ownership model, that you don't have to allocate the memory. So what does a garbage collector really mean, you guys, since you're moving in Rust? I don't understand why they can't do the types without the garbage collector.
Yeah, I haven't read too much into that either. I would argue that the reason Rust works so well with WebAssembly is just because they put like a real dedicated effort into doing it. Like they have entire working groups in the Rust, whatever the Rust community is, whatever. They have entire working groups dedicated towards like WebAssembly. And so so like, I don't quite understand either, like what the restrictions are, like why they can't do what they're doing. Like the laws of non-gen thing actually implements a bit of a memory allocator because that's how it does the passing of data back and forth WebAssembly directly. So yeah, I haven't like read the details about why that's a restriction or not, but yeah, like everything I've seen in terms of what language works best for WebAssembly, it's like mostly Rust just because they're the ones focusing so much on it. They're the ones that put so much effort into like making it work and providing these toolkits to allow you to modify Rust code and use any language.
What kind of insights do you have when you're running code in WebAssembly? Can you actually, assuming you're not going to be able to run a debugger check?
Yeah, not great. So you can call, you can import functions from JavaScript into WebAssembly and then call them. So I mean, you can do console logs in WebAssembly and whatnot. You can call it alert from WebAssembly if you want. So there are ways to do that kind of debugging, but in terms of like, I brought up the like the Chrome debugger, like when I'm running through WebAssembly, and it's like, hey, this is on a WebAssembly thing, and it's like, you click and it's just like, yep, there's no man's land, like there's no so like I haven't dug into it too much just because it hasn't been a problem for us yet. It hasn't been like why is this like completely crashing, but I don't think it's great yet, right? I think it's like there's a WebAssembly text format, which is WAT bot. That's like an S expression style code, and so I think that's like the best way to get because that's essentially like you can write a plot directly if you want, but it's that's sort of like the closest thing you have, like just above the binary code there. So it's not great. I mean, you could do it, like I said, if you really have to like console log stuff, you can, but it hasn't been a problem for us yet, at least.
Yeah.
It's mostly been things on like if it doesn't work, it doesn't compile kind of stuff.
Sure.
There's been a couple things where you try to run stuff because there'll be certain Rust libraries you'll import that use like C code. They're like you would expect to have like C things, and so like you have to get rid of all that and leave all that stuff out because you know pure Rust in order to compile it to WebAssembly. And so luckily a lot of libraries will provide WebAssembly alternatives to their libraries that, or they'll provide feature flags that say like, hey, don't use this because I can't for my environment, whatever it is.
Do you see any improvements in like memory consumption, or does it use more?
We haven't really profiled that yet. Like, it certainly probably uses more than the JavaScript stuff. Well,
yeah.
If it was like, if it was like handwritten JavaScript, it would probably be quite a bit better memory consumption of JavaScript than it would be WebAssembly because of all the data copying you're doing there. But with the scala-head stuff, like, who knows? I mean, that shit is not great. Like, there's, it's like basically having to like compile the entire Java ticket library of JavaScript and run it there. So I mean, it's probably worth noting that like, I mentioned basically that the scala-head library we ended up, it was somewhere like between 400 and 500K of JavaScript code. Our WebAssembly binary is, I think I made some changes today, it's like 600K, but it's also binary, so like GZIP's way better. So like even when you load it, it drops down to 215 or something like that, and we haven't come like put a ton of into like try to really strip it out. There's a whole bunch of like tools you can do like hacking and like try to reduce your code size. But we're basically in that part of the reason we have those performance numbers is because like we're going to want to get a ton of stuff when we compile it. We're basically saying like I don't really care about size, I care about performance, right? And so like inline's a ton of shit. And so there's a balance there of like, well, do you want a larger file size, faster performance, or do you want, do you want it to be smaller but also slower? And so, our thought is that like it's pretty decent how it is now, at least like, I mean, no one said like we're not going to give you money for this because it sucks. It's like we're still installing it where it's like it's functional, sure, but sure. Okay, I had kind of one other thing to talk about and show while he was here. So, a couple questions for everybody. Who has used GPT? Knows what GPT is? Really actively use GPT? Okay, how many people use something like 1Password or that kind of thing, like to be able to like share secrets at work? I mean, personal is fine too. How many of you have stuff in Google Drive, like your corporate Google Drive, like you really probably shouldn't be able to see that's like that. Okay, so we recently open sourced a command line tool called Dynamically after the transformer. So this is essentially kind of a NPM module that is sort of meant to be like a, I mean, we really built this as like a proof of concept of what our technology does, but it's kind of like a better version of GPG than what we consider. And so I don't suspect, we don't have like a lot of huge companies here at Bozeman, but you know, one of the problems with like GPT is that you encrypt files to a bunch of people, and on the team, you say like, okay, engineering like needs access to this file, you encrypt this file to all the people in engineering, right? And that works, except now one person gets fired or leave, right? Now we have to like now take that file and remove it from the shared access, decrypt it, and then re-encrypt it to the new people without that person, right? And like you have to do that for every single file, you have to encrypt it to all those people. It's not super maintainable. And so this is sort of a like it's a similar. It's not as bad, but like things like 1Pass or whatever 1Pass, all those things. They kind of do things like shared AS keys where it's like somebody got removed from this. So like you don't like decrypt and recrypt all the files, but you're sharing keys, which is not super great. If someone like took that key, they obviously get removed. So we released this tool, which is just like I said, an NPM package that allows you to more easily manage the files and share them with groups and modify who has access to those groups. So you can kind of see from this example here, you can create groups. So we would say, let's create an engineering group. And then we have a file. We're going to encrypt this file to the engineering group. And so now you have your secrets.json file. You can shut that up on your drive or whatever shared file sharing thing. And then after we put that file, we can add members to that group. So when you add members by email, this is all email based. When you log in this tool, you just log in and you do it and then you can share it with people. So it's we don't actually do anything responsible for actually sharing the file. It's like up to you to take the file and disseminate it however you want to do that. So we add members to this group. At that point, once all those members are out of that group, they can all share, they can all decrypt that file. And so, you can file decrypt that file. Cache is just actually stand out, and so it just runs that file. So at some later point, if you want to revoke someone's access to that group, you just remove that user from that group, and that's it. All the files don't have to be touched at all. So you don't have to go like scouring all the different places for that because the file you decrypt it and that user do it. You modify users in the group at orthogonally to who you actually put the file. So I can encrypt the file and hire 20 people in my team. And all I have to do is add to that group and they all encrypt every file that's been encrypted to that group. So anyway, I just wanted to kind of put this out there and it's just a really kind of like a proof of concept tool that we built. And we use it internally.
What is the email validation happening?
Email validation.
Yeah, like how do you know that they are that user?
What's like the login process?
So when you install it, there's a you start at I9 login, and that pops a browser that we just do an auth0. I don't know what auth0 is, but whatever. And then you log in, it's like a auth flow essentially. And so the other thing that this supports is devices. So you have a master key that's for your account, and you create a key for any device you want. So you have a work laptop and home laptop, those would have different device keys, and you can revoke those devices at any time. And so you could say, okay, well, somebody stole my work laptop, I'm going to revoke that device, and at that point, that device can't encrypt any other things that are can't encrypt any files that user can encrypt. you know, I don't want to like spend the entire time kind of going through like everything this thing supports. But you know, you have like file commands, group commands, log in, log out. So if I do like so I have like 2 machines right here that I've logged in on, and it says like, okay, you have here's when it's created, here's when it's best updated, like, and then which one's the current device. And so I can basically say like, I user device delete. It's like 3. And so now like that device, if somebody had that, they try to do file decrypt, they would go up to
So this is network dependent, though, right?
it would look, yeah, it is.
That's in the same APIs that the other Iron Core libraries work for
Yeah,
the key
yeah, it's
storage
all
and
the
stuff.
same. It's, I mean, this is basically just like tool built on top of our SDKs and whatnot. But, you know, like point being here is that it gives you kind of better like control and access over what files you have. It's a lot more scalable, right? I mean, if you work at a big enough company like when us works at like right now, Oracle days, it was, you know, people were kind of like getting tired of leaving like all the time. And you got to like decrypt every single file, decrypt it to people every time. It would be a real pain in the ass. And it's also not using like shared key, right? So it's not like every single file is encrypted with the same like AS key or anything like that. It's all they're all different. So anyway, I just think that if you want to check it out, feel free. It's just all the instructions are here on this repo.
Are you the main committer?
I think I might be the only committer.
There's only 7 commits. So.
Yeah, well, like, we basically, like, I mean, the way we do everything is like we commit to a private thing and then like, okay, we want to open source it, so then you like, you all the history and everything. So, also merge commits, and so.
So there's actually like 3 commits.
No, like.
There's 6 branches.
Sorry, squash commits only.
Okay.
Sorry, no merge commits. Yeah, so there's like actually only, like, you know, there's probably like 50 commits. So anyway, that's all I had. So thanks everybody for coming out. Thanks for